Our next topic that we will discuss is called accumulating functions. And what we'll be doing with accumulating functions is if we want to figure out how much of something that we have, if you are mainly looking for an amount that something changes by, that is important for us because when we need to find that amount, we can integrate the rate at which it is changing. So if you needed an amount, you integrate a rate. So here in example 1, if water is being pumped into a tank at this rate per gallons per minute, then the amount of water, so you're looking for an amount that is pumped in for the first 5 minutes, is this. That's all you have to do is integrate that rate. And the same is true. Part B is another good example. So we're talking about velocity, and it's in miles per hour. So if you want to know distance, then you're going to integrate that rate. So another way to write this is going to be your accumulation function will look something like this. F at A, that you're given here, that's going to be your starting amount. And that's usually given to you somewhere, somehow, it'll be given to you. And this portion here is what we'll be substituting in values for x. And we will be finding some bounded area again. Okay, so referring back to example 1, if there's 120 gallons of water in the tank, in the first example, find the total amount of water in the tank after 5 minutes. So the setup here, that total number of gallons, is going to be how much you're starting with, and then I'm going to integrate that given rate to find how much water is in the tank after 5 minutes. So here we would have to integrate, and just a quick review of integrating this. The square root, if we're integrating the square root of t plus 1, again, we would probably do some kind of u sub, and then we would have to find du dt, which is just going to be 1. And so notice that we do end up with a nice sub. If we solve for dt, that's going to be 1 times dt, or just dt. So we're really integrating the square root of u du, and that's going to be u to the 1/2. So let's think about that 1/2 exponent. And so you're going to have u to the 3/2 and 2/3 in front. And you can adjust your endpoints if you want to. This is going to be evaluated from, well, I'm going to take 5 and substitute in, so that's going to give me 6. And then 0 substituted in is going to give me 1. So we're going to have 120 plus what we get when we integrate, which is going to be 2/3 times 6 to the 3/2 plus 2/3 times 1 to the 3/2, or 2/3. And if this was free response, you're welcome to leave it like this. If not, this would have been a calculator problem. And so this would give us approximately 129.131 gallons is how many gallons we would have after 5 minutes. Now for our second example, same idea, but we're going to say that a car is 57 miles from its starting point, and then it's going to travel for 3 hours. Now how many miles is it from where they started? So we're going to have 57 plus, and then we need to integrate and find this value. So when we integrate, remember that is t cubed over 3. That's going to give us 3t squared plus 12t. And again, we are integrating from 0 to 3. And so we would have 27 plus, and then we're going to sub in 3. So that first one's going to give us 9 plus 27 plus 36. And then minus our bottom endpoint with that 0. So that's just going to give us 0. So when we add all that up, we should get 100 and 29 miles. So this is a great application for our antiderivative. We're looking at those accumulation functions. All right, now let's look at this geometrically, because this is a classic problem that you're going to be asked, and you'll see this quite a bit. Now, the first thing they're going to want us to do here is find all of these different values. So in other words, starting out, we will need to go substitute in and find our bounded area. So it's more practice with what we've already talked about, which is good. So for our first part, we're completing this table. So if our input value, in other words, what I'm subbing in for x is 0, notice we are integrating from 0 to 0, which gives us 0. If we substitute in 1, we need to integrate from 0 to 1. So in other words, I'm finding this bounded region here. So we need to go through and find that area, and this area here, that is the area formula for a rectangle. And so that's going to be base or length times width, either one, base times height, it's all the same. So it's going to be 1 times 2, which is 2. So I know that area is 2. Now let's go and look at number 2. Now we're going to be integrating or putting in the value of 2. So I'm going to sub in a 2. I'm integrating from 0 to 2. Well, I already know from 0 to 1. So really all I need to do now is find from 1 to 2, and then we add those. That's why this is called accumulating. So notice here we do have a trapezoid. And so the area of a trapezoid is 1/2 the height times the sum of the bases. So inside here, this region that we're finding, let's label our side values. So this base here, from here to here, that side length is 4. And from here to here, the side length is 2. And the height, this is on its side, the height is 1. So to find that, we have 1/2. I'm going to move down here where I have some room. So I have 1/2 the height times the sum of the bases. So that looks like that's going to generate for us, let's see, 6/2 times 6 is 3. So I know in this area we have 3, but now I have to be careful because I'm integrating from 0 to 2. So I have to add or accumulate both areas. So that's going to give me 5. Now let's move on to our next one. Now we're going to look at g at 3. And so I'm going to go from 0 to 3. So now I've got this other portion over here that I've got to find. So this looks like a triangle, 1/2 base times height. And so we need to look inside this region here. And if I do 1/2 base times height there, the base is 1, the height is 4, so 1/2 times 4 is going to be 2. So now from 0 to 3, I'm going to have 2 plus 3 plus 2, so that's going to give me 7. All right, now let's go look at g at 6. So g at 6, that's going to kind of change a little bit. Now I'm going to be way out here. So I'm going to have, you can either divide this up into a triangle and a rectangle, or you can just do a trapezoid again. I do the trapezoid, and we do need to know that trapezoid formula, so it's going to help knowing that. This is going to be flipped over. Here's one base from 3 to 6, so I know that base is 3. And then this is another base down here. That's going to be a length of 1. And the height looks like it's going to be 2. So again, that formula is 1/2 the height, so 1/2 times 2 is 1, and 1 times the sum of these two, so that's going to give me 4. So I know this region inside here is 4, but it is bounded below the x-axis, so remember we did assign -4 to that region. Okay, so now g at 6, we're going to be integrating from 0 all the way to 6. Well, I know from 0 to 3 is 7. And so 7 minus 4, that's going to leave us with 3. So I know G at 6 is 3. Now let's look at G at 7. And again, same routine here. And so I'm just adding the smaller portion here. So we can do 1/2 base times height again. And so notice the height here is 2. The base is 1. So 1/2 base times height, that's going to leave us with a 1. And it is bounded underneath the x-axis. So really I can look at this value and subtract the 1 from it because we are accumulating. And so that's going to be 2. All right, so there's all of our values. Now let's look at our next question. Over on part B, it asks us on what intervals is G increasing? Now keep in mind G is representing all of the area that we found. And so the area that we found is increasing from 0. We're starting at 0. All of this is increasing until we get to 3. So I can make the statement that G is increasing over the interval from 0 to 3. Now, a little bit of reminding here. If G is increasing, then we always said that that means that G prime is positive. And this is going to tie in a huge concept for us here. In other words, what we can say here is that if G of x is defined to be the accumulating function from 0 to x of f at t dt, then G prime at x, if I do the derivative of this, remember that undoes all of this. And really, what's going to happen is that G prime is going to become f at x every time. And then now let's keep in mind that f at x, well, that's really just the function that we're given. F is the function over here. So let's see if that makes any sense. Well, going back over here, G would be increasing when G prime is positive. Well, G prime is equal to f of x right here. So yeah, G of x is positive, or G prime is positive from 0 to 3. So hey, that's pretty good. That connects a lot right there. And we'll talk about this. We'll practice this a lot more. Where does G have a maximum value? Well, let's go back over here and look. Where was that maximum value? That maximum value occurred at, well, if my pen will write, at x equals 3. The maximum value was, or well, I guess it's present, is 7. That was the highest value we had. Now it wants us to sketch a graph of G of x. So now we can't go real crazy with our sketch here because we only know a handful of values for it. So in other words, it wants us to sketch this input-output function. In other words, you're going to think of x comma y here. So we have the point 0, 0. Then we have the point 1, 2. So I'm over 1 up 2. And then I have the point 2, 5. So over 2 up 5. 3, 7. Now, we can't fool ourselves into thinking that this is linear because we really don't know what it is. But we're just going to try to keep a good idea. 7, 2. So we should have some kind of curve, and y'all know how awesome my drawings are, so just bear with me. We have something that's going to look like this. Now, we don't know any other points other than what we're given, and so we can take our best guess at it. All right, let's move on to another problem and keep practicing. Okay, so kind of the same idea here. We're going to look at what happens geometrically whenever I have an f of x is equal to, same idea here, we're still talking about this bounded region. And so we're going to let k take on a bunch of different values here. So let's look and see what we can plug in and get. So for our first one, we're going to let x be 0. And so we are integrating from 0 to 0. So do keep in mind that. It might be helpful. I'm going to write in a t-chart for us down here, kind of what we're looking at, because we're going to have our x and our f of x, and we have to make sure we understand we are finding the bounded area there. So from 0 to 0, for the first one, we are just integrating from 0 to 0 of f at t dt. And so that's really not going anywhere. That's going to have an area of 0. Now for the next one, we're going to integrate from 0 to 1 of f at t dt. So we're going to find this really tiny triangle under here. So from 0 to 1, I'm looking from here. So really, I'm looking at this little area inside here, which again is still 1/2 base times height. So the height is 1, base is 1, so it looks like we're going to have 0.5 or 1/2 for that bounded region. All right, now let's go look at from 0, we're now going to integrate from 0 to 2 f at t dt. And again, we are still just adding right along to what we've had. So let's look at this region here, which looks strange, but it is a trapezoid. We can look at that as a trapezoid again. And we have our base, which base 1, base 2. So I know that side length is 2, this side length is 1, the height is 1. So again, I'm finding just this region inside of here. So we're going to have 1/2 the height, which we said was 1, times the sum of the bases, which is 3. And so that's going to give me 1.5 for that little region, plus the half we already had. So that's going to give me 2. Okay, now let's move on to 3. So we're just increasing here. We're going up a little bit each time. So I'm going to integrate now from 0 to 3, f at t dt. And again, 1/2. Our base again is 1 times the sum of our bases. So again, we're looking at this trapezoid area right here. And notice these y values. That's what's given us our bases. I don't know if y'all have connected that yet, but that is going to give us our base lengths. And so the distance on the x is the height, which is 1. So we're going to have 1 times the sum, which is 3 and 2, which is 5. So we're going to get 5 over 2, which is going to be 2.5, 2.5. But now, again, we're starting all the way back at 0. We're including this plus all of the previous. So if we go back, that's really 2.5 plus what we already had, which was 2. So that's going to give us 4.5. And then let's look at integrating from 0 to 4. So again, we're just continuing on with that trapezoidal shape here. I'm just trying to get this to change back over. There we go. So we have, again, this portion here, which we are going from way up here all the way down to here. So again, to get those base lengths, we're really just looking at our y values to get our height. Look at the distance between the 2 points on the x, which is 1. So we're going to have, let's see, f at t dt. So I have 1/2 times the height times the sum of the bases, which is really your y. So that's going to give me 7. So 1/2 times 7 is going to be 3.5, but it's still plus what I already had, which is 4.5, because I'm integrating from 0 to 4. And so that's going to give me 8. All right, so notice that again, we are accumulating, we're gathering up all this information here. Now let's see if we can answer some of the questions over here. And the first thing it's asking is, what is the domain of f? So what is all of the possible x values for f? And that's going to be from 0 all the way out to 10. So our domain is from 0 to 10 in points included. All right, so now look at part C. They want us to use the concept of area accumulation to complete a graph of f. Plot the points in your table in blue. So we can go through and plot those. I don't know if that's really just necessary for us to do. We can, but again, I don't see the point in that. So let's just go ahead and continue on with D. Where is the 0 of f? So in other words, where does f end up being 0? Well, let's go back and look. Look at our table of values. We saw that f was 0 right here. Now that's not always going to be the case, but it is there. So that tells me that I know that f is 0 when x equals 0. Now, what is the total change in f? Now, the total change in f, that means that we are going to say f started at 0 and it's going to stop at 10. That's your total change. So it's going to look like f at 10, that final value, minus the starting value. That's your total change there. So we need to calculate that. So let's go over and we need to find our value at 10. So I'm going to go back over here and let's find what would f at 10 look like. So that's going to be our integral from 0 to 10, f at t dt. And so we need to find this bounded area here. Let's find that area. So that's going to give me, let's see, 1/2. We've got to find just that small region. Our base, so that's going to be 1, 2, 3, 4 times our height, which looks like it is 3. So that's going to give me 6. And notice that it's talking about our total change. Now I understand that underneath here, this is -6, but you're talking about a total change here. So we're going to say that we actually have a total. We know we started at 0 and we're stopping at 6. So let's see, f at 10 is going to be 6 minus 0. So that's going to give me 6. And again, that's for our total change. All right, so let's look at our next question. How does total change compare to a net area bounded by the graph of the function and the x-axis? So there's no difference there. These are the same. It's just like talking about a distance versus displacement. Distance cannot be negative versus displacement may be. So here again, your total change cannot be any different. Now, what would be the maximum value of f? So I need to go back and find that maximum value. So let's see if we can figure that one out. And it looks like that maximum value, looking over here at our graph, it looks like we're going to have to calculate what's going on over here, simply because I know that this is positive and it is still gaining some value, and I have not found this particular value right through here. So it looks like we're going to have to do another 1/2 the base, and the base length is 2 times the height, and that height is 4. So it looks like we're going to get 4 for that region. So it looks like we now have enough that we can go through and see what is that maximum value going to be, and we should be able to add up. We know here at 6 we're going to have 4 plus, And let's see, I knew all the way to 8 already. If we go back to our table, we knew at 4, like this whole big portion right here, we knew that whole thing there is 8 plus 4 more. So that tells me that the maximum is going to be 12. And where does that maximum value occur? Well, it occurred at 6. All right, so now let's look at part I. And it says, well, what is the range? What's the set of all of the output or the y values? Well, those y values for f, and I know this looks really strange because it's not necessarily on the graph we're looking at. We're looking at the bounded area, and the range for that bounded area started at 0. That was the smallest, and it went all the way through that accumulating. It goes all the way to 12. All right, so let's continue working. Okay, so example 5, where is the 0 of g? And the 0 of g is talking about what number can I plug in for x, and when I integrate from 3 to this number, I get a 0. So that really looks like that x is going to be 3. Okay, now for the next question, it asks us what is the value of g at 0. So here, to find the value of g at 0, we would need to sub in 0. So I'm going to work that out up here. G at 0 is going to be the integral from 3 to 0 of f at t dt. And we see that our endpoints are inverted, so we do need to do that negative and flip those around. So that's going to be negative the integral from 0 to 3 of f at t dt. And we found that earlier. If you look back up, we found that value right here from here to here. That's 4.5. But then this negative is going to make that negative 4.5. So we need to be careful that we realize that the 0 of g is not necessarily 0 itself. This time it occurs at 3. Now the domain of g, all of the x values that we can consider for g, we can look and see that that's going to be from 0 to 10 again. There's all of our x values. And then what is the total change in g? So while we're talking about our total change in g, we need to keep in mind the domain because that total change is going to occur over the domain. And so we need to find the value for g at 10 minus g at 0. Now we already know what g at 0 is from earlier, so now we need to find g at 10. So I'm going to go back and write in what that would look like. So I'm going to move down here to my graph, and g at 10 is going to be equal to the integral from 3 to 10 of f at t dt. Remember, we had that t value or x value that we're filling in. So I need to go from 3 all the way out here to 10. So I can find this region down here pretty quickly. I'm going to go and find this just because that's a little easier to find. So that's going to be 1/2 base times height. And so let's fill in those values. 1/2, the base is 1, 2, 3, 4. The height is 3. So that tells me that region is 6. Now, let's see, this other region is weird. So I'm going to divide it up into two different regions here. I'm going to have here, we're going to have our triangle, and then here we're going to have a trapezoid. So let's go ahead and find those two different areas. Let's do the triangle again first because that's a little bit easier. So we're going to have 1/2 the base times the height, which was 4. So that region is going to be 4. And then our other region right here, that's going to be a trapezoid because of that funky side there. And let's see, this value is 4 up at the top. This value here is 3, and the base or the height is 1. So the area of the trapezoid is going to be 1/2 the height times the sum of the bases. So the sum of the bases is 7. So that's going to give me 3.5. All right, so going out from 3 to 10, we have 3.5 plus 4. So that's going to be 7.5. So I have 7.5, but then I have this bounded region below, so I'm going to have minus 6. So that's going to give me 1.5. Okay, so now over here, we're going to go through and put all this together because I need G at 10, and G at 10 we found was going to be 1.5. So I have 1.5 minus G at 0, which we found was negative 4.5. So then that's going to give me a total of 6. All right, so now let's look at part E, the maximum value of G. The maximum value of G. So we've got to go back and see if we can find, well, what's going to be the largest value we can possibly have for G. And we know that from 0 to 3, we have a negative value. And so we have to be careful here because I know, and I'm looking down here at this graph, that this region here, that was negative. That was going to be what we found earlier, G at 0, and that was going to be from 0 to 3. That was a negative value. So we didn't start becoming positive till I was in this region here, and we were positive through this entire region. So really that bounded area is the maximum value of G, and we just found that. That maximum area was 7.5. Okay, and where will that occur? Where did we have that maximum value of 7.5? Well, that was when we looked at our bounded region to 6. We expanded all the way over there to 6. So here, where will it occur? At x equals 6. Now, what is the range of G? So what is the smallest value of G we could possibly find? Well, I think that was this negative bounded region, or no. Let's see, what was the biggest negative? It was negative 4.5. That was the largest negative region that we had. And then it's going to go all the way up to positive 7.5. Okay, and then now let's look. We don't want to sketch here. We don't have to talk about sketching that in green. So let's see what else they have for us. Okay, so describe the relationship that when K takes on different values. When K takes on different values, we have a different transformation going on. So here, all of these values right here, this is going to be a vertical shift each time. And we would see that if we took time to plot those points and see, but I'm not going to go through and plot that. Now the next one, at what point must lie on the graph of any given family member? So it's talking about of this. So it's talking about, okay, what value should always lie on there? And it's going to be from that K value up to a 0. So here, K comma 0 should be on all of them because it's going to have a 0 there somewhere. So when the lower bound is K, the area from K to K is 0. So that's going to be what it's talking about. And again, let me go ahead and write that in. Well, if my pen would work, that would be wonderful. So when the lower bound is K, then the area from K to K, so we're going to call it the area. I'm going to run out of room from K to K equals 0 every time. All right, so now let's look at K. As K takes on different values, the function f from K to X graph as vertical transformations of each other. So here we have a vertical transformation. My pen is protesting today. It's a vertical transformation of one another, each containing a particular point that's going to be K0. Okay, and then it says even though the lower bound changed, is f prime of x still equal to f at t? Very important, and the answer is yes. Always remember that if we can. All right, so for example 6, we are shown below a graph of the derivative of f for some function big F, and we're given this value. So what this is going to be really hinging on us knowing is the fact, and it's all the way back at the very beginning, that if we integrate from a to b of f at x dx, that's going to give us our original function back. If we integrate a derivative, we get our function back. And since we have endpoints, we always did the top endpoint minus the bottom endpoint. So that's what this is contingent on us remembering. Now this portion here is going to be something that we're given that we need to incorporate, and we'll set up some kind of equation to solve. So if I know f at -3 is -8, I'm going to have to use that somewhere. Now I'm trying to find f at 2. And now this is not talking about, oh look, right here's 2 and I get 0. That is not what it's talking about. That tells me I know f prime of 2 is 0. This is the derivative. This is the graph of it. So what I need to do is somehow figure out, well, I need to incorporate -3. So I need to set up an integral of some sort, and there's not much room here. Let's see if I can go over here to the side. So I need to set up an integral that's going to help us find 2, and I'm going to use what I know, which is -3. So I need to integrate from -3 to what I'm looking for, which is 2, and I'm going to have to integrate our given function here. So it's going to be f of x dx. So this is going to have a twofold meaning. So for the first part, I know that's going to be equal to f at 2, which is what I'm looking for, minus f at -3, which I'm given. So here I'm going to have f at 2, don't know what that is, what I'm looking for, minus an f at 3 I'm given, so it's -8. So I know f at 2 plus 8. Now, if I knew what this was, then I could solve this equation and find f at 2. And it just so happens, look over at your graph, they did give us information to find the bounded area from -3 to 2. So here's -3. So -3 all the way over to 2 is going to be 10 plus 26, which is going to be 36. And again, we're applying what we know this means to have the integral from -3 to 2. We're finding that bounded area. And so to finish this problem, I'm going to subtract 8 over. And so I see that 28 is equal to f at 2. So we found that answer. Over here is going to be 28. So we're going to have to employ that same reasoning to do part B. So again, let's go through and see, can we set this up? So we're looking for f at 6. And so we're going to have to try to set up some value to find that f at 6. So let's see, we could integrate and use what you know. This is what we're trying to find. Here's what we know of f at t dt. And so that's going to give me f at 6, which is what we're looking for, minus f at 3, which we know is -8. So I'm going to go ahead and put that in. Now we've got to go back and add up. What do I know the bounded region from -3 to 6 is going to be? So from -3 to 6, well, it looks like we're going to have a lot of values here. Let's see if we can't go through and add up. So from -3 all the way over to 2, we know that is 36. 2 to 8 or 2 to 4 is -8 because it's below the x-axis. And then from 4 to 16, we're told that is 14. So all of that is equal to f at 6 plus 8. Okay, so let's see if we can figure out our values here. So 36 minus 8, that's going to give us 28. 28 and 14, let's see, 28 and 14, isn't that going to be 12? 42, isn't it? And then 42, we're going to have to subtract this 8 over. So let's go ahead and subtract that 8. And so that looks like that's going to give us 34. Is going to be f at 6. So f at 6 going to be 34. Okay, and again, we're going to set up the same thing for f at -5. So way back over here is -5. And so let's see what we can do for that one. And we're going to set up the same process. And I'm just going to work it out up here. We know that we're going to be integrating from -5 to -3 of f of x dx. And that's going to give us f at -3 minus f at -5. Let's see what we know from -3 to -5. That's going to be 18. So we know that much is 18. It's going to be equal to -8 minus f at -5. So we're going to add our 8 over. So that's going to give me 26 equals negative f at -5. So we're going to move that negative over, and so we have -26. All right, so now let's interpret some of what they're giving us. Notice that in part D, it tells us that since the area under F is positive on the interval from -3 to 1, we know that the graph of F must be doing what? Well, that graph must be increasing. And that, again, is because what we're given is the derivative. This is the derivative. F prime equals lowercase f. So if our derivative is positive, our function is increasing. Now look at E, very important concept again. Since the area under F accumulates at an increasing rate, we know the graph of F must be, so we're talking about a rate of a rate. So then F must be concave up. Again, that's talking about a second derivative. So now let's look at F. The area under F from -1 to 2, so we're looking at from -1 to +2, accumulates at 8, and notice it's decreasing there. Notice that is the area that's bounded is decreasing. Okay, so it's decreasing rate, so F must be, so we're talking about the rate of a rate, so F is going to be concave down over that interval. And whether or not we sketch here, I don't care if we sketch this one or not, so y'all don't worry about part G.